Welcome to Lasea class. I am your teacher, Jan Lasea. Today we are going to learn floating point in Win32 Assembly Language. A floating point number consists of up to 64 bits of mantissa, a sign bit, and a 15-bit exponent, totaling to 80 bits or T byte or 10 bytes. The processor contains a set of 8 internal floating point registers. The registers are organized into a stack, with ST at index 0 referring to the register on top of the stack, and ST at index 7 referring to the register to the bottom of the stack. When data is read in from memory, it is pushed onto the register stack. Data written to memory is popped off the register stack. The processor contains many instructions for manipulating data on the stack. These instructions include the standard add, subtract, multiply, and divide operations with 80-bit precision, as well as logarithms, square root, loading useful constants such as pi, and others. Computations are performed quickly because the processor was specifically designed for floating point number crunching. The floating point instruction set are categorized. The first category is data transfer instructions. Under this, the following are the instructions for data transfer, such as FLD source that loads real number and pushes into the top of the floating point stack. Another is FILD source that convert integer to float and loads and pushes into the top of the floating point stack. FST destination store real number or decimal number to the specified destination. FIST destination store integer number to the specified destination. FSTP destination store real or decimal number to the specified destination, and it will pop out whatever the value from the top of the stack. FISTP destination store integer value to the specified destination and pop out whatever the value from the top of the stack. The next category is Arithmetic Instructions. Under this, the following are the instructions for arithmetic computations, such as FADD destination source. It will calculate the sum of the value of the destination and source, and it will store the sum to the specified destination. FSUB destination source, it will subtract the value of destination by the value of the source, and it will store the difference to the specified destination. Another FMUL destination source, it will multiply the values of destination and source, and it will store the product to the specified destination. Another FDIV destination source, it will calculate the quotient of the value of the destination, and it will divide it to the value of the source, and the quotient will be stored to the specified destination. Another, it will calculate the absolute value using the FABS. Another, it will calculate the square root using FSQRT, and so on. The next category is constant instructions. Under this, the following are the instructions for loading constant values and push at the top of the floating point stack, such as FLDZ that loads and pushes the value 0 at the top of the floating point stack. FLD1 that loads and pushes the value 1 at the top of the floating point stack. FLD pi that loads and pushes the value of the pi 3.14159 at the top of the floating point stack, and so on. The next category is processor control instructions. Under this, the following are the instructions for processor control, such as finit that initializes the floating point unit, free with specified register st with specified index that will set the floating point register to empty, fwait that waits for all pending floating point exemption handler to complete. The next category is Transcendental Instructions. Under this, the following are the instructions for computing trigonometric and logarithmic functions, such as fp sine that will calculate the sine, fp cos that will calculate the cosine, fp tangent that will calculate the partial tangent, and so on. To better understand on how to use the floating point instruction set and also the role of the floating point stack, let us examine some example codes. Let us convert 100 degrees Celsius into its equivalent Fahrenheit temperature using the formula Fahrenheit is equal to the quantity 9 divided by 5 multiplied by Celsius to be added to the constant 32. In the data segment, I declared some memory variables such as the variable Celsius, assign a double word data type, and initialize to 100. The variable 5, assign a double word data type, and initialize to 5. The variable 9, assign a double word data type, and initialize to 9. The variable 32, assign a double word data type, and initialize to 32. Finally, the variable Fahrenheit, assign a double word data type, and it is uninitialized. In the code segment, the finit command initializes the floating point unit. The next command, fld Celsius, loads the value of the variable Celsius, which is 100, at the top of the floating point stack. The next command, fmul9, multiplies the value of the variable 9, which is 9, to the top of the floating point stack, the value 100. And the product, which is 900, is stored and replaced the value of the top of the floating point stack using this formula. St at index 0 is equal to st at index 0 multiplied by the variable 9. The next command, fdiv5, divides the value of the top of the stack by the value of the variable 5, which is 5. And the quotient, which is 180, is stored and replaced the value of the top of the floating point stack. Using this formula, st at index 0 is equal to st at index 0 divided by the variable 5. The next command, fadd32, adds the value of the variable 32, which is 32, to the top of the floating point stack, the value 180. And the sum, which is 212, is stored and replaced the value of the top of the stack using this formula. St at index 0 is equal to st at index 0 plus the value of the variable 32. The next command, fst Fahrenheit, copies the value of the floating point stack at register st at index 0 to the variable Fahrenheit. Therefore, the variable Fahrenheit contains the value 212. Let us study and examine another example. The following codes will compute the area of the circle having a radius of 5.6. In the data segment, I declared the variable radius, assign a double word data type, and initialize to 5.6. The variable area, assign a double word data type, and it is uninitialized. In the code segment, the finit command initializes the floating point unit. The next command, FLD radius, loads the value of the variable radius, which is 5.6, at the top of the floating point stack. The next command, fmul radius, multiplies the value of the variable radius, which is 5.6, to the value of the top of the floating point stack, which is 5.6. And the product, which is 31.36, is stored and replace the value of the top of the floating point stack. Using this formula, st at index 0 is equal to st at index 0 multiplied by the value of the variable radius. The next command, fld_pi, loads the pi constants at the top of the stack. And the value 31.36 will adjust and move to the next slot at the floating point register st at index 1. The next command, fmul, with no arguments, multiplies the value of the top of the floating point stack at register st at index 0 with the value of the next slot underneath at register st at index 1. Therefore, it multiplies 3.1415 and 31.36. And the product, which is 98.52, is stored and replace the value at register st at index 1. Using this formula, st at index 1 is equal to st at index 0 multiplied by st at index 1. The value of the top of the stack, which is 3.1415, is popped out. Therefore, the value 98.52 moves up one slot and now is at the top of the floating point stack. The next command, fst area, copies the value of the floating point stack at register st at index 0 to the variable area. Therefore, the variable area contains the value 98.52. Last example. Let us compute the hypotenuse of a right triangle with the value 3 for side A and value 4 for side B. Using the formula, hypotenuse is equal to the square root of the sum of the squares of the value of A and B. In the data segment, I declared the variable A, assign a double word data type, and initialize to 3. The variable B, assign a double word data type, and initialize to 4. The variable H, assign a double word data type, and it is uninitialized. In the code segment, the finit command initializes the floating point unit. The next command, FLDA, loads the value of the variable A, which is 3, at the top of the floating point stack. The next command, fmul A, multiplies the value of the variable A, which is 3, to the value of the top of the floating point stack, which is 3. and the product, which is 9, is stored and replace the value of the top of the floating point stack. Using this formula, st at index 0 is equal to st at index 0 multiplied by the value of the variable a. The next command, fldb, loads the value of the variable b, which is 4, to the top of the floating point stack. Thus, the value 9 moved down one slot at register st at index 1. The next command, fmul_b, multiplies the value of the variable b, which is 4, to the top of the floating point stack, the value 4. And the product, which is 16, is stored and replace the value of the top of the floating point stack. Using this formula, st at index 0 is equal to st at index 0 multiplied by the value of the variable b. The next command, fadd, with no arguments, adds the value of the top of the floating point stack at register st at index 0 to the value of the next slot underneath at register st at index 1. The sum is 25 and stored and replace the value at register st at index 1. Using this formula, st at index 1 is equal to st at index 0 plus st at index 1. The value of the top of the floating point stack is popped out. Therefore, the value 25 moves up one slot, and it is now at the top of the floating point stack. The next command, fsqrt, computes the square root of the value at the top of the floating point stack. And the result of the square root of 25 is 5. And it is stored and replaced the value of the top of the floating point stack. Using this formula, st at index 0 is equal to the square root of st at index 0. The next command, fsth, copies the value at the top of the floating point stack at register st at index 0 to the variable h. Therefore, the variable h contains the value 5. I made a user-defined macro to help us process some conversions and initialization. The macro string to float with arguments source and destination converts a string into a float. For example, string to float input str variable a converts the string value of the variable input str to float value and stores to the variable a. The macro float to string source decimal places destination converts a float into a string. For example, float to string variable h to variable str value converts the float value of the variable h to string and applies two decimal places format and stores the string result to the variable str value. The macro memset destination car count initializes a variable with a character. For example, memset offset input str space character length of the variable input str initializes the variable input str with space characters, and the number of space characters depend on the length of the input str. Let us put up an actual code for the hypotenuse of the right triangle example. The program prompts the user to input the value of side A and side B as decimal numbers and calculates and displays the hypotenuse. In the data segment, I declared some memory variables to display prompt messages such as please enter the value of side A, please enter the value of side B. Output memory variable message such as the hypotenuse is, and some other memory variables to hold the value for the input side A, input side B, and the computed hypotenuse. I made a procedure input that prompts the user to input the values for side A and side B of the right triangle. Inside the procedure input, this command will display please enter the value of side A. The command readline input str will input the user for the value of side A. The string to float will convert the string value entered into a float value, and it will be stored to the variable A, the value of the side A. It is important that we need to call the memset to reinitialize the input str so that the next input will function properly. This command will display the prompt please enter the value of side B. This command readline input str will allow the user to enter the value of side B. The string to float command will convert the entered string into a float value and store the float value to the variable B containing the side B that is entered by the user. The procedure process computes the hypotenuse using the floating point instruction set. I already explained these codes a while ago. The procedure output displays the hypotenuse. First, we need to call the float to string to convert the float value of the variable h into a string value, having a 2 decimal places format, and then the result will be stored to the variable str value. The print output str will display the message the hypotenuse is, and then the print str value will display the value of the variable str value containing the hypotenuse value. The main procedure where our program starts to execute by the CPU. This command will display the program title hypotenuse of a right triangle. This command will call the procedure input. Next, it will call the procedure output. And next, it will call the procedure output. And here is the complete source code of the hypotenuse of the right triangle. These are the declared memory variables that I presented a while ago. This is the code for the procedure main, the code for the procedure input, the code for the procedure process that will calculate the hypotenuse of the right triangle, and the code for the procedure output that will display the hypotenuse. Let us run and test. I press Ctrl R and then type the command m-prog. I will input the value of the side A, which is 3, the value of the side B, which is 4, and then the computed hypotenuse is 5. Let us run again. This time I will enter the value for side A, which is 2, the value of side B, which is negative 5. The value of side A is positive 2, the value of side B is negative 5, and the hypotenuse is 5.39. And the result is correct. That ends our topic for today. I hope you have learned in my class. Thank you for watching. God bless us.